Let's talk about frames and machines. So far, we looked at trusses, we looked at beams, and if you think about this, these are two different types of structural elements. Trusses are only in tension and compression, and the forces are only applied at the end of the elements. These are called two-force members. Beams can have forces in the middle, and in this case, they're called multi-force members. Now, the way I like to think about frames and machines is to think that we can have a combination of two-force members and multi-force members in the same system. Trusses are two-force members again, and beams are multi-force members. In the case of machines, we're going to have things that are mostly moving. In the case of frames, we're going to have things that are mostly stationary and they are resisting loads. But the way of analyzing them are exactly the same. So an example of a machine might be this, where we can see it moves, right? It has a purpose of moving, but we have different structural elements. This is an structural element right here. There is another one right here, and it's connected by pins, right? So depending on the location of that structural element and the forces applied to it, we might have two-force members or multi-force members. If we put something here to cut, we're going to see that these long elements on the sides are going to have one force, the one coming from the thing that is cutting, another one from this pin, another one from this pin. So in that case, these long elements are going to be multi-force members. In the case of this element over here, it's only going to be a two-force member because it is only having the forces by the two pins, this pin and this pin. So this particular system is a machine because it moves, and it can be analyzed using statics by breaking down the different elements and analyzing the different elements. Frames are a little bit more difficult to show you because they are usually much larger, right? So, but we have frames in buildings all the time. Now, let me tell you a general description of how to analyze these type of systems. So when we look at frames and machines, remember, just kind of to tell you this again, or to write this down again, frames and machines. We have that frames are usually for static loads. And frames are used quite a bit during buildings and stadiums and things like that. In terms of machines, are systems that move, and they're used, for example, to cut things or to load things and things like that. So those are moving. Now, the key for this is to be able to break down the system and its components and analyze each of the components. So the key for analysis is to break down the system and the components. So in a way, the way that we did trusses by the method of joints is not much different than we're going to do in terms of the analysis of frames and machines. The difference is that some of those elements are multi-force members instead of two-force members. So let me give you the general idea through a very short example. We're not going to do the math on the example, but just the concepts of how to analyze a frame or a machine. So let's say that we have the following frame. Let's say that we have something like this. Let's say a pin over here. These are all pieces of wood, okay? And we have another piece of wood somewhere in here. There you go. All of those are connected by pins. And we have some type of a load. Let's say that this is one of those systems you might see in the movies where the trains are picking up the mail or picking up packages, right? So we have some type of the mail, something hanging in there. All right, so let's look at what's happening in this system. And the first thing I like to do when I'm analyzing this type of systems is to identify which of these elements are two force members and which of these elements are three force members. So as a reminder, the two force members are something like truss members, where they only have forces at the ends and they're connected by pins. So they do not have any bending moment, right? So in internal forces, they're only tension, compression. They're only normal forces. So let's start with the with this member over here. Let me see. So this member over here, I can see that it is only connected by pins, and it does not have any forces in the middle of it or at the end. So in this case, this is a two force member. Right, two force member. The only way that that element is in equilibrium is because it has two forces that are in same magnitude and opposite direction. They have to be along the line of that element. Otherwise, the element cannot be in equilibrium. Now, let's look at the horizontal element. This element over here, it has pins, right? So it is connected by pins, but it also has a force right here. So in that case, it is not a two-force member. This is a multi-force member. Okay. Same thing as this one. So when we look at this vertical element, we're going to see that when we do the free body diagram of that vertical element, at the bottom we have a fixed connection, and that fixed connection is going to have two reaction forces but also a moment. So we're going to have some forces at the bottom, we're going to have some forces at each of the pins. So this one is also a multi-force member. So that's the first thing that I try to do. I mentally try to look at which of those elements are two-force members, which one of those are multi-force members, right? The next step that I try to do is I take each of the components of this frame or of the machine, and I try to do a free body diagram for each of those components. So what I'm going to do is I'm going to put some letters here. I'm going to call these A, B, and C for each of those joints. Oh, that's not working very well. Let's see. A, B, how about here? B, that better? Nope. Nope. My pen is failing me today. Okay, so let's see. B over there. Ah, that's better. So that's B. And then in that corner, we're going to put C. Okay. That's probably a little better. Okay, A, B, and C are those three joints. And then what I'm going to do is I'm going to do a free body diagram of each of the elements, but also as each of the pins. Okay, so my free body diagram for my vertical element, I'm going to do, I'm going to call that AB, just to put a name to it. So I'm going to have my structural element. At the bottom, I'm going to have a moment. I guess I should call this over here D, right? So this is MD. Then I'm going to have some forces at A, and one of the key aspects that we can determine by thinking about which of those elements are two force members is we actually know the direction of that force at A because it is connected to that blue element, right? So we can actually say right away that this force at A is somewhere in this line. It's along the line of that element AC. Okay, we know that angle. So What I mean by that is that if this is theta, that means that this angle over here is also theta, because that blue element is a two-force member. Okay, now at B we have a connection with a multi-force member. Is a pin, so I know I have two forces, but I don't really know what is the angle of that force. So I'm just gonna write two forces. So in this case we're gonna have, let's call this FA, let's call this FBX, FBY for my axis, X. I'm gonna go with Y somewhere over here. That's all right. And that's my free body diagram. Now I have too many unknowns. I have, by the way, I forgot two more forces, right? I forgot my reaction forces at the bottom. So I'm gonna have a, let's call it, put it over here, a FDX and also an FDY. So I have 1, 2, 3, 4, 5, 6 unknowns. Way too many to be able to solve with a single free body diagram, right? Okay. So what I need to do then is keep going and do the free body diagrams for the rest of the elements. So I can do, for example, my free body diagram of A. And that is the joint that we have right there. So if this is A, now this is a particle. And for that, we're going to have a force coming from the blue element and a force coming from the red element, right? Those are going to be, for this to be in equilibrium, the only option is that they are the same magnitude and opposite direction. There is no other possibility for that particle to be in equilibrium. Okay, I'm gonna keep going. I'm gonna do my free body diagram of AC, that is that two-force member that we highlighted in blue. So my free body diagram of AC is gonna be something like this. All right, we're gonna have a force that was coming from that place, from A, and there is a force. It has to be in the other direction, right? So this is FA, this is going to be FC, right? The only way that two-force member is in equilibrium is that FA to be equal to FC. So as you can see, as I draw more free body diagrams, what I'm starting to do is to try to find some additional equations that I can use to be able to add to the number of unknowns that I have in my first free body diagram, right? All right, let's keep going. So that is my free body diagram of AC. I'm gonna put some axes. I forgot my axes here, X and Y. And of course, if I have dimensions and angles, I will add those as well, just to have a complete free body diagram. We can do my free body diagram of C. I'm gonna do that under here. Free body diagram of C. All right, that's that joint on the top right. And this is connected to that two-force member, so that means that I need to have a force coming from that two-force member, this one over here. I need to have the reaction at the at C. So this is C. I have a force FC, and then the other way for this to be for this to be in equilibrium is to have a force that is in the opposite direction, same magnitude, axis. And now I have my free body diagram of BC. That's that vertical or horizontal element at the top, right? Okay, so I'm gonna have my weight, which would probably be known for this problem of that box. I'm gonna have my force at C. That will be going the opposite direction, so we'll be going this direction, right? FC. And now since I know this angle is theta, the same angle as we had here at the top, so this angle over here should also be theta, right? Also be theta. And then I also have my two forces, right? My two forces of Fbx and Fby, right? I'm drawing them in that direction because I already decided a direction for that element AB, and the ones in element BC are going to be in the opposite direction as the ones that I defined previously, for this to be consistent, right? All right, very good. So once I look at all those free body diagrams, including the free body diagram of B, I want to forget about that. And that we're going to have Fbx, Fbx, Fby, and Fby. Once I look at all of these free body diagrams, my key is going to be to then start looking at which of those I can start answering questions. In a nutshell, which of those have I have enough information and have enough unknowns for me to be able to solve. The first free body diagram, as we talked about, has too many unknowns, right? So in this case, I'm going to have this Fdy is an unknown, Fdx is an unknown, this moment Md is an unknown, Fa is an unknown, Fbx is an unknown, Fby is an unknown. So way too many unknowns. I cannot start with that free body diagram. Fa has two unknowns. I don't have any information to add to that free body diagram, so I cannot start right there. Fc also has two unknowns but not known quantities, right? So I will not start there either. Free body diagram of C, same situation. I have two forces that I don't know, so I cannot start there. Now, when I come to the free body diagram of BC, I can see that I have 1, 2, 3 unknowns because I know W, right? W is the load that I'm applying to that frame. So in that case, I have a free body diagram of a rigid body in which I can formulate three equations of equilibrium, and I should be able to find those three forces. Once I'm able to find those three forces, I can go back to the other free body diagram. So for example, I will go back to the free body diagram of AC, and I should be able to find Fa. Once I have that, I can go to the free body diagram of AB, because now I know Fbx, Fby, and Fa, and I should be able to find the reaction forces Fdx and Fdy and Md. Now, the other free body diagram that we can use is the free body diagram of the whole structure. So I can actually do one of the whole system and also find those reaction forces and start in that location. So in a nutshell, the key idea of this analysis of frames and machines is to be able to break down the system in other free body diagrams, and I start looking at the number of unknowns that are available in each of those free body diagrams. And then you can start piecing the information together to be able to solve for the unknowns.